Welcome. Today's notes worksheet is entitled Radian Measurement of Angles. And so we've actually already had a quick introduction to what radian measurement would look like. And obviously we'll just continue that conversation today. We'll do some investigations and some examples, and we'll tie the two units together. So degree measurement of an angle and radian measurement of an angle. So it looks like I have on your paper a little investigation to get us going. And by the way, you do need some type of flexible ruler for this. A CSAP ruler would be fine. And you also need a compass for this one as well. So those would be the two things that you'll need especially for this investigation. So make sure you have those available, and then I'll sketch a couple things in and we'll see what we can do. So it says on your paper, is radian measurement dependent on the size of the circle? So I guess what we want to do initially is just draw an angle in place, and let's see what that would look like. So how about this, everyone? Give me an initial side going out that way. That would be great. And then however you want to do it, it's totally up to you. But from the vertex, let's get a terminal side in there. And we're going to just sort of include this as a rotation from here to here. I'm not going to draw that in, but I do want to kind of talk about that theta right in there. Now, what we're going to do here is measure this in radians. And so you have your sketch on your paper. And what I would like for you to do at this stage, and I'm going to do it freehand, so it's not going to be great, but I'll see what I can do for you. Everybody, you're going to take your compass, and you're going to put the compass point right on the vertex right there. Then you're going to put the pencil point anywhere on the initial side. Your choice. It makes no difference. So again, compass point right here, pencil point anywhere on the initial side, and then if you can please sketch out a circle for me. And again, this is not going to be pretty, but something like that would do. All right, so we have a circle here, and if you remember correctly, our theta in radians is based on the ratio of the arc length of the circle to the radius of the circle. And so what I'm going to ask you to do, everybody, is put a little R1 right in there. So a little R1 for the first radius, as we're going to do this a couple times at least. And then everybody, I want you to put an S1 for the arc length up there. So R1 and S1. Now this offers up a nice review from the previous notes worksheet. If we want to go ahead and get a measurement for theta in radians, what we want to do here, of course, is take the S value and divide it by the R value. So in this case, guys, because we're going to do the measurement, I need you to actually use your flex ruler and measure the arc length of the circle, then measure your radius, and then you're going to grab your calculator, and of course, remember, theta is a ratio of arc length to radius, S over R. And so you're going to take a moment, pause the video if you get an opportunity, and actually calculate the measurement of your angle in radians. So take your S value and divide it by your R value. And then just kind of put it right in there. That'll just be our first answer. And that should be the measurement of your angle. S divided by R. All right. Now I will assume at this stage everybody does have their angle measure for whatever you drew. And then what I'm going to ask us to do now is a secondary circle. So everyone, if you go back to your drawing right here, I need you to put that compass point back on the center. And then please your pencil, run it along anywhere you'd like. It makes no difference. Anywhere along the initial side. And I need one more circle. So I'll do my best here. You guys, yours is going to look quite a bit better than mine. But something like that would do. And if you notice, of course, I have a radius. So I'm going to call that R2. And everybody, I have an arc length. That'll be S2 right up there. And, of course, what I'm going to ask you to do is measure your angle using those two quantities. So I'm going to come over here. In fact, I'm going to kind of do this as theta 1. Actually, no, that's not a great idea. Let's just do it as theta. And then S2 over R2. So everyone, you may need to pause the video for a moment, but you can see certainly where this is going to be headed. I'm going to ask you to take your second arc length. So your S2, that would be from here to here. See if you can get your flex ruler in place to do that. And then your second radius, for me that would be from here to here. And you're going to take those two values and divide them. So grab your calculator after you've written both those down, and you're going to divide them. And of course you're going to get an answer. You can just kind of put it right in there. And the question, of course, is, do you get the same number? Now, it might not be perfect, but if you did S over R for this particular theta, and for the one that you drew on your paper, no matter how many times you do S over R, it should be the same. And so I can have a very small circle, a very large circle, because we're talking about the ratio of those two values. As long as the terminal side has not changed, and there it is, everyone, there is my terminal side in a nice uniform position right there. No matter how many times I do S over R, I should always get the same result. So the investigation question, let's go ahead and go back and answer it. It says, is radian measurement dependent on the size of the circle? Absolutely not. No, no, no. It's only dependent on the position of the terminal side. So no matter what, theta is going to be S over R. And that would be the case. Now just one thing to kind of go back into from the previous notes worksheet, and then we'll go ahead and do example 1 right here. In fact, you'll see this again on example 1. But remember what you did, either inches or centimeters probably, but whatever the case may be, when you calculated your S and you calculated your R and divided them, notice what happened to the units. They canceled out, and you end up getting just some real number. It's unitless. And so that's what a radian measurement is. It is literally just a real number. And I think I alluded to this on the previous notes worksheet, but it opens up an entire branch of trigonometry. As a matter of fact, it's called the trigonometry of real numbers. And we're going to do a lot with that over the course of this unit. Okay, well let's do example 1 now that we've got a feel for it and hopefully solidified some ideas from the previous notes worksheet. So example 1, a central angle theta in a circle of radius 3 inches intercepts an arc of length 7.5 inches. What is the radian measurement of theta? Perfect. Well, everyone, I'm going to just kind of sketch out what I believe this would look like, and you don't have to necessarily even draw a picture with this. We can get it to work no matter what. But essentially, it should basically look like that piece right there. Whereas if I tracked a point kind of going around, get something like that, that circular path, this arc length right here, everybody, I think I saw as 7.5 inches. So the terminal side and initial side intercept an arc length of 7.5 inches. And the radius, of course, is 3 inches right in there. And I didn't draw this perfectly by any means, but you can kind of see if this length is 3 inches right here, going around 3, and then, and basically going from here to here, roughly speaking, would be about 7.5. Okay. Well, obviously, guys, don't overthink this. It's pretty straightforward at this point in time because we know our theta is just a ratio of the arc length to the radius. And so in this case, I have my 7.5 inches. And I'm going to divide that by the 3 inches right here. And you could see, again, just the unitless piece, inches cancel, and I end up getting 2.5 as a value, and that's it. So you can write this a couple different ways, by the way. Our answer is definitely on the board. You could just write it as theta equals 2.5, and without the degree symbol, and this is key, everyone, without the degree symbol there, this is known to be a radian measurement of an angle. Obviously, everyone, 2.5 degrees is quite a bit different than 2.5 radians. So this answer tells me it's in radians because there's no little degree symbol by it. You could put a little or here if you want. Sometimes people put a little RAD on the back here, just more as a placeholder, just for emphasis, 2.5 radians there. But either one, theoretically, is correct. So pick your poison, so to speak. Okay, so example 1, S over R, everybody. Okay, well, I think we're getting into the time here where we want to start connecting the two measurements. So we have the degree measurement of an angle, and we have now the radian measurement of an angle. And the easiest one to kind of connect would be the 360 degrees. And we'll see why that is momentarily. So here's what I'm going to do. It says find the radian measurement of an angle that has a degree measurement of 360. Let's take a look and let's kind of sketch that out there. So there's my initial side. Everybody draw the initial side if you get an opportunity. And let's have that terminal side rotate off the initial side, counterclockwise, of course. And you could see if it rotates counterclockwise, if I was to track a point on that terminal side, form that nice circular path and kind of go back. And as a matter of fact, 360 degrees basically would look like that, where the terminal side would be exactly on top of the initial side right there after one full rotation. And we're going to use exactly that premise momentarily, but here's what I would argue. That theta, as we all know, is S over R. Now what's special about the 360 degrees? Let's figure it out here. So the easy one to put in, everybody is R. Everyone throw a little radius in place. The secondary piece, of course, is talk about the arc length of the circle. Now here is the question. What is special in this situation with the arc length? What does that arc length actually represent in terms of this circle that I drew on the board? And if you think about it, if you look at it hard, it looks like the arc length of the circle is actually the entire circumference of the circle. And so if that is the case, well, if it is the circumference of the circle, we do know the circumference of the circle actually is 2 times pi times r, by definition. And then all of a sudden, you can start to see some numbers form. So what, again, makes this occur is that the arc length is the full circumference of the circle. And that is 2 pi r. And if I asked everyone to simplify, those r's would cancel. And lo and behold, everybody, we have our connection between degrees and radians. 360 degrees is exactly 2 pi radians. And that's what we have to work with. Okay, so I hope everyone's clear on why that plays out, being the full circumference right there. Hopefully my drawing did it justice. So here is the deal. Everyone, if you would, I need a big asterisk on that piece right there. We have to start connecting these, and these are some of the special angles that we're going to see over the course of this entire unit. I'm going to have to get very, very comfortable with this. So let's start that out, everyone. First and foremost, 360 degrees we now have as 2 pi radians. Exactly, precisely, leave it as such. And as we work our way down, we can start to use that idea to build on some others. So if 360 degrees is 2 pi radians, I'm hoping everyone would be in agreement that 180 degrees is exactly pi radians. So if you can envision that 180 degrees, and you don't have to do this on your paper, I'm just kind of thinking out loud here, but basically 180 degrees would look like this. There is my circular path from here to here. That would be the S. That would be the R. If I took S over R, it would always be exactly pi. Okay, I'm going to erase that just so it doesn't get in my way, but that would be the case. 180 degrees is exactly pi radians. Again, let's continue to expand on that. So 90 is really half of 180, so should be half of pi. Typically, you guys, we're going to say that as pi over 2. So 90 degrees is exactly pi over 2 radians. And let's go ahead and do the 60 then. So 60 degrees, the way I'm envisioning this is 60 degrees is a third of 180. And so it should be a third of pi. Everybody, we're going to pretty much read that as pi over 3. So 90 degrees, everybody, is pi over 2. 60 degrees is pi over 3. Let's continue. Again, these 45s come up a lot. So here's 45 degrees. I see 45 degrees as half of the 90. And so half of pi over 2 is going to be pi over 4. And so 45 degrees is exactly pi over 4 radians. Okay, last one to kind of take care of here, which would be the 30 degrees. Maybe you're starting to guess exactly what this is, but 30 degrees, I would argue, is half of 60. And so half of pi over 3, everybody, is going to be pi over 6. And those are the big ones right there. You're going to really, really need to know that table very well, including a bunch of the multiples for us to be successful in terms of the next step and the next step and so forth. So let's read through it just one time and give you a sense of what it's going to look like. So 360 degrees is exactly 2 pi radians. 180 degrees is exactly pi radians. 90 degrees is pi over 2 radians. 60 degrees is pi over 3 radians. 45 degrees is pi over 4 radians. And 30 degrees, everybody, is pi over 6 radians. And so what we can start to do now, as it says on your paper, we can start doing some easy conversions just using multiples of those numbers in the table. So we're going to do that on example 3 here. It looks like the top 4, we're going to go from radians to degrees, and the bottom 4, we're going to go from degrees to radians. So here's how I would argue it. 2 pi over 3, this is an angle that's going to come up quite a bit for us. Well, 2 pi over 3s, everybody, the way I see it from the table is 2 60s. There's pi over 3 right there, and we have 2 of them. So 2 60s, and 2 times 60, everybody, is 120 degrees. If I asked you to envision 2 pi over 3 radians at this point, knowing that it's 120 degrees, you could probably tell me it's up in the second quadrant like this. And again, I won't make you envision all these, but something like that. That would be 2 pi over 3 radians right there. And this would be the rotation on it. Good. Let's do part B. 3 pi over 2. The way I read it is each pi over 2 is 90 degrees. And we have 3 of them, so 3 90s. And as you can see, 3 times 90 should be 270 degrees. So if I asked you to envision 3 pi over 2, should be able to at this point, something like this. Again, just kind of thinking out loud. That would be the rotation for 3 pi over 2. Again, a lot in trigonometry. There is a lot of memorization, but more than that, there's really a lot of visualization. Can you see it in your mind's eye? And these are just some numbers that come up time and time again. Well, let's do the next one. Letter C, 11 pi over 6. Each of those pi over 6s is 30 degrees, and so I have 11 30s. And 11 times 30 would be 330 degrees. So you can see 11 pi over 6 is a quadrant 4 angle. Okay, next one over here, let's go 3 pi over 4. And again, the way I read this is each pi over 4 is 45 degrees. Told you we're going to see a lot of multiples of that 45. And so 3 45s, everybody. 3 times 45 would be 135 degrees. So if I asked you to envision 3 pi over 4, that's going to be the one that's splitting that second quadrant right there. There's 3 pi over 4 with that rotation. So there's some good ones just using the table, of course. Please, as you start to see these, really recognize them and be able to envision them. All right, let's go degrees to radians on this bottom set right here. In this case, everyone, I have 300 degrees. And I guess the way I would argue it is 300 is a multiple of one of these numbers up here. Actually, it's a multiple of 2 of those numbers, but we would pick the highest one there. And I see it as a multiple of 60 degrees, and I hope everyone's okay with 300 degrees being 5 60s. So 5 times 60 is 300. And as a result, by the way, you would see this as, if it's 5 60s, it's 5 pi over 3. So I'm hoping you all know where 300 degrees would be, if you can envision that one, and 5 pi over 3 would be the radian equivalent to that. By the way, I've seen this in past years. Some students will do it in terms of it being a multiple of 30, and don't write this on your paper, but they would say something like, oh, this would be 10 30s, which would be 10 pi over 6s, and that's exactly right. But as you can, of course, see, reducing 10 pi over 6, and you definitely have to reduce this. 10 pi over 6, as you can see, really is 5 pi over 3. So this is the answer we're looking for right here. And as a matter of fact, we do want this as an improper fraction. So 5 pi over 3, please. All right, 210. We have to kind of figure out what it's a multiple of here. The way I see 210, it looks like 210 would be 7 times 30. And so as a result, everybody, 210 degrees, understanding that piece, is 7 pi over 6. Good. Again, see it. See 210 degrees. That's also 7 pi over 6 radians. 225, this is a good one. It's tough to know the multiples of 45, but you'll see this time and time again. 225 happens to be 5 45s. So a multiple of 45 degrees, and if it's 5 45s, then everybody, it's 5 pi over 4. So 225 degrees is the angle that splits the third quadrant, and so you can envision 5 pi over 4 doing the same. Last one for this example set here, letter G is 240 degrees, and everybody, I get 240 as 4 60s. So 4 times 60, really, 4 pi over 3. So see the 240 degrees, that rotation counterclockwise, that would be exactly 4 pi over 3 radians. Now these are some of the ones that come up time and time again, so please take a look at them, really recognize them, and envision them certainly. I'm going to go on to my next page right here, and what we're going to do is potentially look at a more formal way to do some of these conversions here. If we didn't see it from the table, or for whatever reason, is there a way to kind of go from degrees to radians and radians to degrees? And so as a matter of fact, what we're going to do is a little more dimensional analysis. So it says it on your paper in bold, formal conversions between the two measurements. And here's the key, everybody. From that table, you could really use any of the combinations. This is the cleanest and most efficient way to do it. Pi radians is exactly 180 degrees. So what we're going to do is dimensional analysis to kind of pull it off. So we're going to multiply by a fraction that has different units but is the same value. So here's what you're going to write in place, and then we'll do the example 4 to kind of back this up. So very simply, to go from degrees to radians, we're going to multiply by pi radians. And again, the RAD is really just a placeholder, not necessary. But if you want to put it in, that's fine. Over 180 degrees. That's to go from degrees to radians. And of course, if that's the way to go from degrees to radians, we would multiply by the reciprocal in order to go from radians to degrees. So on your paper, if you can you please write multiply by, and we'll go 180 over pi. So I'll be asking you about this as you go through some of the independent work is it pi over 180 or is it 180 over pi? So start getting comfortable with seeing this conversion as this, and this conversion, everybody, as this right here. And obviously we'll do an example set to kind of back that up. So example 4 on your paper, it says convert the angle measurement, express your answer in exact form, and just maybe make a little note here. Exact form, kind of remember this from geometry, is leaving pi in there. So exact form is not trying to let the calculator approximate pi and getting a decimal approximation, but leaving pi in as an irrational number. So let's go for it. So 20 degrees, let's see what that would be equivalent in radians. And so in this case, 20 degrees, to go from degrees to radians, as it says, I'm going to multiply by pi over 180. Those two things right here, they are the exact same number in just two different measurements. And so really, I'm not changing the value of what I start with. I'm just changing the units of what I start with. And you could see, of course, that the degrees will cancel, one on top, one on bottom. And I end up getting, in this case, 20 pi over 180. Which again, it's a legitimate answer, but I'm really going to ask you to make sure you reduce fractions completely. And so if I reduce 20 over 180, it would be 1 over 9. So as a matter of fact, again, pi over 9 would be 20 degrees. Okay, so please express it something like this, if at all possible, as opposed to something like this up here. If it can be reduced, please reduce it. You see a lot of patterns with these denominators here and their position on the coordinate plane, and so we really need to make sure that they're reduced properly. Okay, let's go ahead and do part B. Part B is pi over 12, and notice in this case I don't see a degree measurement right here, and that's how I know. That's really the only way I know that this is a radian measurement of an angle. And so in this case it's going to be radians to degrees, and so it's 180 degrees over pi radians. Again, if you want to put a little RAD here, that's perfectly fine. This radians, that would be right here, would cancel out with this radians up here. And I end up getting a couple things that cancel out, and this should work out nicely. Just these pi's cancel just from what I see. And you end up getting 180 divided by 12. And if you were to actually take 180 divided by 12 on the calculator there, should be 15 degrees. And if you look at that table, I think we probably could have speculated that 15 degrees and pi over 12 would be the same angle in two different measurements. Okay, good. Well, everyone, let's keep going. Part C, degrees. I want to go radians. Okay, so degrees to radians here, which means we're going to multiply by pi over 180. Again, degrees, degrees, cancel. And as you can see, I end up getting 48 pi over 180. I definitely see that being able to reduce here. So I'd ask you actually to pause the video, take a moment, see if you're okay with the fraction component to this. see if you can go ahead and reduce that and get it in exact form there. So pause for a second and pull that off for me. Okay, well, when I did this, I figured that actually 12 goes into both of those. I think that's the greatest common factor of 48 and 180. So 12 goes into 48 4 times, so it's 4 pi. And 12 goes into 180 15 times, so it's 4 pi over 15. Good. So 48 degrees is exactly 4 pi over 15 radians. Okay, 2 more to take care of here. Radians to degrees. Again, back and forth here, everybody. Radians to degrees is multiplying by 180 over pi. Again, if you want to put the RAD here and the RAD here, that's fine. They cancel, of course. I get a couple things that work out pretty well here. The pi's will cancel in this case. And let's see, I get 180 times 4, and then divide by 5. If you do that, you end up getting, what's that, 720 over 5, which would be 144. Keep the unit with it, and it is in degrees. So 4 pi over 5 is 144 degrees. All right, so I'm hoping, kind of switching back and forth, you're really sort of seeing the dimensional analysis in action and being able to go from one to the other. Let's go ahead and get the 13 degrees right here. And think to yourself, is it pi over 180 or is it 180 over pi? And to get rid of the degree symbol and change it to radians, the only way that works is to do it as pi over 180. Because now the degrees will cancel, and 13 pi over 180. And that's it. That actually is probably as far as we can go in terms of exact form. The next stage, I believe the next example, will be to kind of multiply that out and then divide by the 180 and get an approximation. But this would be the exact angle measurement, leaving pi in place. All right, very good. So let's take a look at the next one. It looks like I have 2 with degrees and 2 with radians there. And I actually like letter D. We'll come back to that piece in just a minute. But it says on your paper, convert the angle measurement and round to 2 decimal places. So I'd actually encourage you maybe to pause the video for this example and do it yourself and see if you can come up with it in each case there. In this case, you're going to let the calculator you're going to use the pi button on the calculator and multiply or divide things out. So pause the video, see if you can pull it off by yourself, and if not, no worries, I'll obviously go through it. Okay, so I'm thinking it would look something like this right here. Degrees to radians, multiply by pi over 180. And in this case, I'll just kind of put an approximate symbol, as we are going to go ahead and multiply it out. Officially, it would be 254 pi over 180, and we would reduce from there. But I'm going to go ahead and bring my calculator up and just kind of let it take over. And I'm going to do exactly this, everybody, and I hope you did the same. 240 times pi, just remember that pi button right there, and then divide by 180. And that's all you have to do. And so in this particular situation, again, it's not exact, but to 2 decimal places, 254 degrees is about 4.43 radians. And again, if you want to put an RAD on the back of it, you're more than welcome to as a placeholder. We'll see that sort of in the next piece that might be helpful. But here, it really doesn't matter. As just a real number right there, that is implied to be a radian measurement of an angle. Okay, and then we can kind of work through a couple of these other ones. Negative 476 degrees. Again, I'm just going to go ahead and do this. Multiply by pi over 180. And when you do that, everybody, you end up getting about negative 8.31 radians. About negative 8.31. Now letter C, look at this one right here. This is an interesting one. Have to be able to recognize and distinguish between the two. 2.476, this is radians because I do not see a degree symbol there. That's how I know. It is a radian measurement. It is just a real number. And so in this case, all I would do to go from radians to degrees, 2.476, multiply by 180, divide by pi. Radians would cancel, and of course it would give us our degrees. So it's about, what do we say here, about 2.5 radians, give or take. 2.476 translates into about 141.86 degrees. Perfect. Now here is a great one right here, of course. 1 radian. And do you remember on the previous notes worksheet, you actually constructed 1 radian here. And so let's see what the degree equivalent would be. 1 radian, I would of course multiply by 180 over pi, 180 degrees over pi radians. Radians would cancel. And officially, the exact answer, I know I didn't ask for it here, but just FYI, the exact answer would be 180 over pi degrees. That actually is 1 radian. Precisely 1 radian. Now, in terms of an approximation, everybody, if you get an opportunity, take 180 and divide by pi on your calculator if you haven't already, and you should get about 57.3 degrees. I've got it like that. I wonder if it's 0 or 1 in terms of the second decimal place. Not that it matters a ton, but about 57.3 degrees. Now, I won't make you do this, but I am just curious. It would be great to see if you go back and if you grab a protractor and you go back to the previous notes worksheet where you actually constructed 1 radian, to set your protractor down and see how close to 57.3 degrees that actually is. And if you did your construction perfectly, remember that the 1 radian was where the radius and the arc length were the same, and that happens in one particular position, no matter what the size of the circle is. It should see that it is really right there. It should be 57.3 degrees, give or take. Exactly 180 over pi degrees. So if you get an opportunity, do that. If not, no big deal. Okay, so let's see. For example 6, I'm thinking you can do this a couple different ways. I'm going to basically ask you to pause the video and try it yourself there. You can probably skip B. I'm not too concerned about that. 30 radians, I'm not too concerned about that. But you should be able to start ballparking some of these numbers and envisioning them. 0.8 radians, where would that be? 3.4 radians, where would that be? 5.9, et cetera, et cetera. Should be able to start to see things a little bit there. So you have a couple options with this before you go ahead and answer all 4 parts. You can convert to degrees for each of these, and based on that conversion, you probably should be able to know which quadrant it's in. So what you could do potentially for 0.8, this is probably the way to do this, you would multiply by 180 over pi, and you'd get a number there, and based on that number, you should be able to know that that is in quadrant 1. So 0.8 radians is in quadrant 1. And that makes sense, right? Didn't we just say that 1 radian is about 57 degrees? And so 0.8 radians has to be, you know, a little below that, so still in quadrant 1. So I would love to leave this one up to you for just a moment and see if you can pull off B, C, and D. Where are each of those terminal sides for those radian measurements of angles? Well, let's see. 3.4, I actually have in quadrant 3. And remember, pi radians is 180 degrees. Now pi is about 3.14. And so 3.4 radians is a little more than pi, so it's a little more of a rotation into that 3rd quadrant. 5.9 I have as quadrant 4. Again, we'll kind of talk about what separates 3 and 4 and kind of going from there, but should be in quadrant 4. A little below the 2 pi radians. Remember, 2 pi would be about 6.28 radians, give or take, and 5.9 is just a little below that. 6.5 radians would be 1 full rotation around, plus a little more, getting into that 1st quadrant. Again, 6.5 is a little more than 2 pi. 2 pi is 1 full rotation around, so 2 pi would be 360 degrees. And so you could see 6.5 radians is just a little more than 2 pi. So hopefully, you know, again, you're starting to really work with these numbers and starting to see it in action. Now this table here, I just sort of put for my own purposes, but I would encourage you just somehow, some way to consolidate some of these. I'm just going to write some of the multiples that we are going to see time and time again throughout trigonometry. And again, if you want to write them down, I think it's a great idea, but these are the ones that you're going to see time and time again. So pi over 6, everybody, 30 degrees. The next one that comes up in quadrant 2 is 5 pi over 6. That's 150 degrees. 7 pi over 6, everybody, 210 degrees. And 11 pi over 6 is 330 degrees. Okay. So again, these are just ones that you're going to see a lot. So just, I don't know if memorization is the best word, but certainly recognition at this point would be a good idea. Now I'm going to go ahead and put a little maybe ... on that as that does continue. But those would be the primary ones that we're going to look at. Okay, and under pi over 4, I would say pi over 4 is 45 degrees. 3 pi over 4 is 135 degrees. 5 pi over 4 is the next big one that'll come up for us. That's 225 degrees. 7 pi over 4, this is a big one too, and that would be 315 degrees. All of these are multiples of 45. Okay, the pi over 3, so I'm going to take care of that over here. Pi over 3 is 60 degrees, of course. Again, just keep on seeing it, keep on thinking about it. 2 pi over 3, we saw that example already, I know. 2 pi over 3 is 120. See that one? Next one that comes up, I think we saw this one too. 4 pi over 3 is 240. And let's see the next one there, 5 pi over 3 would be 300. Again, I'll throw a little ... on these. Obviously, remember, an angle can be any real number, so these continue as the rotations continue around. But in terms of going one primary rotation counterclockwise, these are the big numbers that come up. Pi over 2s, yeah, we do know now that pi over 2 is 90 degrees, and 3 pi over 2. That's the other big one there. We saw that as 270 degrees. ... Theoretically, we could start talking about 5 pi over 2, and 7 pi over 2, and 9 pi over 2. We could talk about negatives, of course. And then let's do the last one here for pi. Pi would be 180 degrees. And 2 pi, of course, would be 360 degrees. And that's, if you remember, is kind of where we started the conversion process. 2 pi radians is 360 degrees. One full rotation counterclockwise. And I'll throw the ... there. We could do 3 pi as 540, 4 pi as 720, etc., etc., etc. So start the process, everybody, of really just learning these numbers and envisioning these numbers. You've got to see that terminal side for these numbers, and there's some great stuff that we're going to be doing. But it all kind of stems from this piece right here. Well, I'll kind of stop it at this point. Of course, as you go through the independent work, let me know if you have questions. And certainly appreciate your patience with this and you taking good notes with it.